AP Chemisters, this is Mrs. Vanderwall bringing you the last edition of the Chapter 16 Blank Wall series. Well, as we know, chemistry, it's a blast.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenoir, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet.
So the question might be, is the reaction of sodium and water spontaneous? And I would say most definitely it is. Why do you think that is? Well, what is Gibbs free energy dependent on for it to be spontaneous? Do you think that reaction was exothermic? It sure looks so. What about the delta S? Do you think that the disorder increased or decreased? We went from a solid sodium and liquid water, and we made aqueous sodium hydroxide and hydrogen gas. If you remember what drives your entropy, the fact that you're making a whole bunch of gas should be an indication that entropy increased. So I thought it'd be kind of fun to start off the last series with something that's a blast. So let's kind of see what's happening in section 16.7. This is the dependence of free energy and pressure. And once again, that we said that enthalpy is not pressure dependent. Back that was delta H, but is entropy pressure dependent? Well, entropy does depend on volume, as you see right here. And if you think about it, if it's dependent on volume, then it will be dependent on pressure. So if you have a large container, you're going to have a lot more randomness. You're going to have a lot more distribution in a sense, and go back to think about the probabilities of finding these molecules. And so if a large volume has a large entropy and a small volume has a small entropy, then because the relationship between volume and pressure is indirect, that we would say that the entropy of low pressure then would be greater than high pressure. If you have a high pressure, you're going to really smush those molecules into a smaller area, and they're going to be less random in that case. So a low pressure, they're quite a bit more random and have a lot more freedom of motion. So in essence, we understand that entropy is dependent on pressure. So how does that relate to Gibbs free energy? Well, we know that Gibbs free energy is indeed related to S from the main equation, where you had delta G equals delta H minus T delta S. So there is that relationship between Gibbs free energy and entropy. And as it turns out, this variation, or excuse me, this derivation of the equation is a little bit more complicated, and I really don't think you need to know how we get this equation. Just look at it and understand that this is the G under certain circumstances that is not standard is equal to the Gibbs free energy that is standard, plus R, which is the universal gas law constant, times temperature, which must be in Kelvin, times the natural log of the pressure. As we're going to see, this idea of pressure would be the same idea as the law of mass action, how we would set up the equilibrium constant. That's what we would set it up as. What is standard? What does this naught mean? Well, G naught is the free energy at a pressure of 1 atmosphere, and then this G is the free energy of a gas pressure at a different pressure, not at standard. This also can be applied for the idea of Q, and we saw Q back in the last section where we were talking about what about conditions that are not in equilibrium. And so we are coming back to that same idea again where, well, if this is at standard form, how does a non-standard Gibbs free energy work? Because not everything is going to be at 1 atmosphere, not everything is going to be at 298, not everything is going to be at 1 molar solution. So how do those conditions affect Gibbs free energy? Well, it all lies right here. So Q again is the law of mass action. R is this gas constant. It's the same one you'd use up here. And keep this in mind. Why are we using the 8.3145 value? Because it has the joules in it. Don't use the 0.0821. There's no joules. Make sure you know when to use the universal gas law in which cases. So your units, joules per Kelvin times mole, is your clue. You have to use that one here. And again, the delta G naught is the free energy for when all the reactants and products are at the pressure of 1 atmosphere, and delta G without the naught is the free energy change for the reaction at different pressures. How does that help us? Well, let's go on and look at the next question. You might actually want to get out a piece of paper because this is actually going to take long. Or why don't you just write really small in the notes that I gave you? Okay, so here's problem number 12. One method for synthesizing methanol involves reacting carbon dioxide and hydrogen gases. So what is the delta G value if you do not have everything at 1 atmosphere? So here your carbon monoxide is at 5 atmospheres and the hydrogen gas is at 3 atmospheres. So we need to determine what is the delta G for these non-standard conditions. Well, the first thing I would do is write down that equation that we just showed you. So there's the there's the equation, and the first thing you notice, we need to solve for G naught. So we need to come up with this. Remember, we had 3 different methods in which we could solve for G naught. The first one is use the equation delta H minus T delta S. They didn't give us that information here. Another one was using like the derivation of Hess's law, and they didn't give us that here either. But what they did give us is the delta G of formation, and that will indeed help us. If you remember that delta G is equal to the sum of the products minus the sum of the reactants, and we can use that then to solve for the delta G naught for the whole reaction. Let me write that down here. So go ahead and solve for delta G naught, and let's see how you do. All right, so hopefully you got something like what I got, where you found your delta G of your products minus your delta G of your reactants, and you just plugged in the numbers, and I got negative 29 kilojoules. Now note what I immediately solved for. I solved it in terms of joules. And why did I do that? Well, because go back over here, the R value is in joules, and you have to have in the same terms. So I just converted this number, negative 29 kilojoules, into joules so I can add it to this number. So let's go ahead and see now what do I have here. So I'm still looking for delta G. That has not changed. I now have my delta G naught of the actual standard reaction. So that's negative 29,000 joules. And now I'm going to add it to R, which is 3145 joules over Kelvin times moles. And then my temperature is 298 Kelvin. And now what? I'm starting to run out of room, aren't I? I need to have the ln of Q. Well, what's Q? Let's go back and look at our balanced reaction here. Our Q is products over the reactants. Remember that? So Q is equal to the pressure of the product over the pressure of the reactants. Well, what is my product? My product's a liquid. Do we ever put a liquid in terms of the K value, the Q value here? There is no pressure for the liquid, really. It's probably just so small we don't really worry about it. We never put liquids in here. So I'm just going to put that as a 1. And then we're going to have carbon dioxide. And to what power do I write carbon dioxide? Its coefficient is 1. So it's carbon monoxide raised to the first. But what about the hydrogen gas? I do have pressure of the hydrogen gas, and I will raise that to the second. So it's the pressure of the carbon monoxide to the first and pressure of the hydrogen gas squared. So let's kind of go down and scroll it down here. And let's go ahead and do that. So ln of Q is equal to 1 over, and they told us that the pressure of the carbon monoxide is 5 atms. And they told us that the pressure of the hydrogen gas is 3 atms, but remember what I have to do? I have to square that. And so then when I put this all together, I need to figure out what that's equal to. Okay, so I found my Q, which is 1 over 5 atmospheres times 3 atmospheres squared, which is 1 over 45, and 1 over 45 is 0.022 repeated. So what is the natural log of Q? Plug in the 0.022 to get negative 3.81. We're not done yet, so now we got to put this all together. So here we go. We're going to have, so delta G is equal to negative 29,000 joules. Yes, per mole actually. I think I left out the mole earlier. Plus 8.3145 joules over Kelvin per mole times 298 Kelvin times negative 3.81. And notice that your natural log of Q is unitless, so the the kelvins cancel out, and all of our units work out really pretty nice. When we put this all together, you should end up with negative, looks like negative 38,000 joules, which is equal to negative 38 kilojoules per mole. And that was per mole too. And that's our answer. So is this reaction still spontaneous? Yes, it is. Okay. All right, well, you probably knew this next section was coming because in section 16.7, we saw where Q was introduced. And Q was the symbol, in a sense, to indicate how close we are to equilibrium. So remember back when we talked about KSP, that if the Q was greater than KSP, then it would be shifting one direction. If the Q is less than KSP, that's when a precipitate wouldn't have formed. So Q is indeed related to K. So in this case, delta G is related to K. And so what we find is that if we have Q is equal to K, that means our system is in equilibrium, that delta G is 0. And what does that really mean? Well, what is delta G? It's free energy. So if free energy is equal to 0, there is no energy available to do work. So let's kind of see how that worked out here. Okay, so we said that at equilibrium, delta G equals 0. We also know that delta G equals delta G naught plus RT ln Q. So if this is equal to 0, I just went ahead and I subtracted RT ln K from both sides, and that's what we end up getting. So at equilibrium, this is our new equation. So watch this. If delta G naught equals 0, then K equals 1. If delta G naught is less than 0, think about what that means. It means it's negative. So if delta G is negative, we know that's spontaneous. We know this reaction is going to go. We know that we are going to make some products. And there you go. So if delta G is or not is positive number, well, what have we said already? If it's positive, then the reaction is not spontaneous. If it's not spontaneous, then you're not going to be making a whole bunch of products. You're going to have a whole bunch of reactants being made. And it's like this. If you roll a ball down the hill, so let's pretend that here's my ball and it's rolling down the hill. So what does that mean? That this ball's energy is becoming more and more negative, if you will. Its potential energy, the positional energy is becoming more and more negative as it goes down the hill. And then all of a sudden, the ball reaches the bottom of the hill. All right, then what? If it's going to go back up the hill, up here, what's going on? It's not going to do that spontaneously. It's not going to be sitting at the bottom of the hill and all of a sudden going up the hill. That's not spontaneous. That is not going to happen. So at the very bottom of the hill, that's where delta G is 0. So here, delta G is negative. here delta G equals 0, and here delta G is positive, which we said is not spontaneous. All right. It looks like this video is about 15 minutes, so I'm just there. I just have a little bit to go to finish off this whole thing, so look for part 2. I'll see you in a few minutes.